What is true about a steam trap? A, B, C, D, or E? What's true about a steam trap? Okay, let's take a look at the results. Do you think there'll be a distribution of results? Professor, why don't you explain this to us before you ask us these questions? All right. Well, the way to answer this question is in your mind. I think a good thing to do is think about a temperature entropy diagram. True? All right. We have two pressures. We have the intermediate pressure, and then we had that low condenser pressure. This one was maybe 20 kilopascal. This one was maybe 1 megapascal, just to throw some numbers around. Okay. What went into state one? What went into the device? Saturated liquid. Saturated liquid. All right? And the flow had to go through a little orifice or a little restriction. It had to drop the pressure. It had to drop the pressure. Okay, so my knowledge about a restriction, maybe this little X in that circle reminds me of a device that looks like this, which maybe every now and then they put a little valve on top. True? Well, tell me a little bit about flow through a device like that. Yeah, you get a pressure drop, but it's not reversible, is it? It's irreversible, which means entropy goes way up. That means that the entropy at 1, it's no way that it can do that. There's no way. So how do we sketch it on a TS diagram? Out to some higher entropy at the exit. Why do I put a dashed line instead of a solid line? Well, that's the convention used in many textbooks and many parts of thermodynamics to indicate a process is irreversible. It's kind of going from state 1 to state 2. We don't know the exact path. It's a dashed line. It's irreversible. So now, could this be true? No. Pressure? Look at the temperature. No. Yeah, this comes in at T1, goes out at T2. It's going to be cooler. The saturation temperature at high pressure, saturation temperature at low pressure. What about this one or this one? I think low pressure probably expands some, right? So, nah. You just guessed it? No, you knew it. You knew it, right? It's isenthalpic process through there. Okay, so it's isenthalpic. That one was hard, but there you go. That's what it is. That's what's happening. The purpose of the steam trap is not to have heat transfer to the room. Sometimes you do have heat transfer to the room. Well, then it wouldn't be purely isenthalpic. But the way we model it, we have no pressure drop through the heat exchanger. We have no heat transfer from the steam trap. We also have no heat transfer from the steam turbines, do we? That's our standard assumptions. So what you can do if you come out of that closed feed water heater, you could put it through a steam trap and dump it to the condenser. Good. One other thing you could do is you could say, well, this is saturated liquid, isn't it? Why don't I put it into a pump to boost it and then throw it into a mix with 7 and 11 and all that, and they're all at the same pressure, and then take it out? That would work too, wouldn't it? It's just that you got to make sure that that pump doesn't run dry. It needs to keep up perfectly with the condensate flow rate. So there have to be some good controls in there. Okay. This is another alternative. You could have a closed feed water heater with a pump. Okay.
Mix, isn't that just an open feed water?
That's an open, just
okay.
Open heat.
It has to be the same pressure.
Yeah, and what happens is these temperatures, let's go ahead and go to a temperature. I think I have one. Yes, I do. Good. But this is with the trap. Let's go ahead and sketch the whole cycle out with a trap. Let's go about 450 degrees C. Let's go around 8 megapascal. There's state 1. Let's put it down to about 1 megapascal. Right there. There's state 2. Let's not worry right now about the feeding that closed feed water heater. Let's go and reheat to maybe state 3. Maybe it's the same temperature, maybe it's a little less. Then go down to the condenser. I think that's 20, that's state 4. Then come across to 5. Then put it through the pump, 6. Then 6, you're going to go through this closed feed water heater. And I'm going to say the temperature at 7 is a little less than the temperature at 8, which is the temperature at 2. Okay. So this is the temperature at 2, the temperature at 8, 295. Oops, it looks wrong. This is steam. Then what's the saturation temperature at 1 megapascal? What's the steam saturation? I forgot that number. At 1 megapascal, it's 180 degrees. So maybe we could specify that this is 175 degrees C, 5 degrees less. That'd be reasonable. So right there is state 7. Right there is state 8. True? Okay. Then we're going to put it through a trap. 8 will kick down and over to state 9, and 9 will also condense just like the condensate from 4. It condensed from 4 over. Okay. Now I have all of these states, do I not? 7, 8, 9, all of them on this diagram. True? Yes.
7 is 8 compressed liquid.
8 is saturated liquid. Saturated liquid. This is either way you would say it's compressed liquid, or I'd probably call it subcooled liquid. It's at a very high pressure, is it not? What's the pressure at 7 compared to the pressure at 1? Yeah, it's the same. So it's at the 8 megapascal. It's hard to show it, all those lines tucked in there, but it's at that high pressure. Now let's change it up. You ready to change it up? Maybe I'll change the color to, I don't know, will blue work or purple? Maybe purple will work the best. Get rid of the steam trap. Come out. I need to move this out of the way. Put in a pump. Put it into a mix. And there you go. So we'll still have 7. We'll still have 8. This 9 is no longer right there, so we'll recycle the number 9. Let's put the number 9 right there.
I have one question actually. You said that pressure at 7 is equal to pressure at 1, but between the 1 and 7 is a steam generator.
Yeah, and the only thing happening in there is heat transfer into the fluid. So it's not a pressure increasing device, it's just a temperature increasing device. Right.
Shouldn't we use 9 after the pump?
You could do that. That would make sense probably to put 9 here and put 8 here. Renumber it a little bit. So now the pressure at 8 is equal to the pressure at 7 is equal to the pressure at 9. They all have the same pressure, true? Oh, I'm sorry. I see what you're saying. Okay, leave it 8 right there. Put 9 right there and make this 10. Thank you. That's what you're saying. Okay. So now I got to back up here. So we have the pressure at 7 equal to the pressure at 10 equal to the pressure at 9. Those are the 3 pressures that are the same. And they're all the high pressure at 1. Okay, well, so what changes here? I don't have this irreversibility going down. I'll leave 7 a little below 8 right here, but when I put it through the pump, where is 9? 9 is right there, a little above the 8, just a little above 8. And now this is a tough one. Where is 10? 10 is a mix of 7 and 9. It's in between them. It's in between them.
Is it close to the 8?
Sure. The 8. The temperature at 8 is less than 9 and above 7. So yeah.
So it's not equal to 8.
No, not equal to 8. No. So, but it could be a little above, a little below, closer to 8 than 7 or 9. Somewhere near. Okay? So right there is 10. Why would you avoid that as an engineer? More complexity, more devices that have to be maintained and backed up. The other one, a little simpler with a seam trap. All right?
Professor?
Yes?
Would stage 5 or 6 be subcooled?
5 would be saturated, right there, liquid. State 6 would be subcooled or compressed liquid. Good? Ready to press forward? Oh, I got to stop asking these clicker questions, don't I? When are you ever going to get your nap? Didn't you pay a university a lot of money for naps? Or not? Come on now. All right, what is the pressure? Think about the 8, the 1, and the 20 kPa, right? 8 MPa, 1 MPa, or 20 kPa. What is the pressure at state 6? Where is state 6? Right there is state 6. So what's the pressure at state 6? 8 MPa, 1 MPa, or 20 kPa? All right, before I show the results, what's the difference between the pressure at 6 and the pressure at 7? It's just going through this one side of the heat exchanger. The same. What's the difference in the pressure at 7 and the pressure at 1? The same. Why didn't you give us those hints before you asked us the question? Because I want to see if you know. So, why is it not 8 MPa, the highest pressure? True? It's 8 MPa. That's a low blow. He asks us questions before we even have a chance to read the book. No, you could have read the book. How many people have been reading the book? I recommend you read the book. Thank you for reading the book. Guess what? You have a competitive advantage over your fellow students if you read the book. Is it unfair? Like, you did something mischievous and, no, that's what people should do. Read the book. All right, let's try this one. Okay, I don't know. Let's do 9. Pressure at 9, state 9. Where is state 9, Professor? I got to find it. Right there is state 9. All right, so it's the low pressure. Congratulations. True? Isn't that the same pressure as the pressure at the inlet and the exit of the condenser? It was 20 kilopascal. Well, we could play more of those games, but let's press forward. We could play a lot of games. You can see I was going to ask a lot of questions, but I think I've already asked a lot of questions. We move into another phase. We talk about working fluids. Water is the working fluid of choice. A couple things. Whatever, you don't have to have water. You can pick another working fluid. We'll talk about other popular working fluids, but think about it. Water is an excellent choice, not because it's just plentiful. Oh, that's one reason it's a good choice. Not just because it's cheap. Oh, it's very cheap. It's non-toxic. Think about that. There's a lot of other working fluids which you don't want sprayed over your body. It's very chemically stable, which means you can pound it up in pressure and pound it up in temperature, and it's not going to disassociate because it is H2O. Oh, Professor, why doesn't it disassociate to H2 and O2 and some other stuff? And I don't know, make that balance like that. Well, it doesn't. You can beat it up really well. It won't disassociate. Some other more complex molecules, you may beat it up, put it high pressure temperature, it starts to break down. It has great thermal properties, not just mediocre. Specific heat, great high specific heat. That means I can put a lot of energy into it. Yeah, temperature go up, but it'll hold a lot of energy. Its heat of vaporization is great. A large HFG at reasonable pressures and temperatures. Thermal conductivity is very good for a fluid. The liquid is very good. Steam is not that bad. And it's very dense. We talk about how dense it is. You can compact a lot of mass and throw it down a relatively small diameter pipe at a reasonable speed. You can get a good mass flow rate because it's so dense in the liquid phase, for sure. But can you use other fluids? Sure. You'll see this term out there. It's an organic Rankine cycle. Now, is that the same Rankine that did the temperature scale that we honor with this vapor power cycle called the Rankine cycle? It is. It's the same individual. So all I did was add this word organic in front of it. Well, it's using the different fluid, a working fluid, which is an organic fluid. Now, how many people have taken organic chemistry? What's the definition of an organic fluid? Has carbon in it, right. Those typically have high molecular mass, high molar mass. What's the molar mass of water? 18. It's 16 for the oxygen and 1 for each of those 2 hydrogens. It's around 18 kilograms per kilomole. You can get high organic fluids with high molar mass of 50, 100, or above molar mass. It has sometimes some very good characteristics, and this is why we pick it, when it changes phase. You need to have it boil, or you'd like to have it boil at a relatively low temperature with a reasonable pressure. And you'd also, the same thing is like to have it compete against water. So it's when they compare it, it's the better fluid for some low temperature sources in which you want to boil water, push it through a turbine, make some electricity, and then condense it again. So maybe you want to burn something, combust something called a biomass. Maybe you have industrial waste heat. They're burning it, they're using it, but it's still warm. They want to do something with it. Somebody told them they could make electricity and sell it, and they might get some tax credits. Great. Maybe geothermal. Maybe not in Texas. We don't have much geothermal potential, but in some mountainous regions, typically where the Earth's magma is closer to the surface of the Earth, Yellowstone and geysers, think of that. Hawaii. You could have some hot subsurface geothermal source. Also solar. This is great in Texas because we have a lot of sun, too much sun, right? In Nevada, desert areas, a lot of sunshine, you could then use to produce a solar pond. Or so especially with low temperature heat sources. If you have a solar concentrator, you probably don't want to go with organic working fluid because you can get the temperature spanking hot, okay, very high. But a solar pond would be one with lower temperature. So you typically want to make electricity with it. Looks like they credit some people back in the 60s with being the first to come out with this working organic Rankine cycle. Same components. Boiler, turbine, condenser, pump. A lot of times they'll pick refrigerant, refrigerant R11. And they'll investigate, well, what type of refrigerant, how would this work in my cycle? Typically, they got to figure out, I have to bring in some heat at this temperature. I have some source of energy, some heat source at some energy. Here I picked 125C just to say, okay, we're going to try R11. We're bringing in energy at 125C. It's relatively low. It's over above the boiling point of water, but it's not really, really hot. Not like 450 when you're burning coal. But we have to throw it away at some temperature. Let's throw it out of the cycle at 25. There you go. 25 in, 125 in, 25 out. So on a temperature entropy diagram for this R11, it's 125 somewhere in here. So you just draw a straight line across. And 25 right there, draw a straight line across. Okay? And so you say to yourself, let's just say that we're going to come out as saturated vapor. There you go. State 1. That's out of what? Out of the boiler, out of the steam generator. Then you're going to pass it through a turbine, isentropic, that would be our best, down to state 2. And from state 2, we'd kick it over to condense it, state 3, pressurize it, state 4, and then heat it up and then go through the cycle. See that? So I said, I need to get the properties. I need especially the enthalpy, and I need also the entropy properties for this R11. Does my textbook have it? But there's software out there. This is the NIST software. I can take you to the site. We can play with it in a second. But I used more time at the first part of this lecture. I was going to do that, but I don't know if I can do that. Maybe I'll come back to it. And I would then say, okay, I kind of fix state 1 by this temperature and quality. I fix state 2 by temperature, entropy. I fix state 3 by temperature, quality. And fix state 4 by temperature, entropy. And now I have all these enthalpies, so I could compute the specific work and the specific heat transfers in the boiler. Wouldn't that be H1 minus H4? And for the turbine, it's going to be H1 minus H. My machine is acting up on me. H1 minus H2, etc. Then I could compute things like the back work ratio, a metric, and I could compute the efficiency, the thermal efficiency. True? But if somebody said, what's the specific work of the turbine, then I got to look through my table and make sure my 2 and all that makes sense. It's H1 minus H2. H1, 448 minus about 401. So it's about 47. Bingo. True? How would I calculate the thermal efficiency of the cycle? The net work divided by the Q in the boiler. True? All that information is available through those enthalpies. So here is a summary for that R11 where I've computed them. The backwork ratio is 2%. The thermal efficiency is 20%. Because you don't have a large delta T, you don't expect high thermal efficiencies. It's almost like you have a free heat source and you just want to try and convert as much of it as possible into electricity and sell it. But you're going to be moving a lot of fluid and moving a lot of heat transfer and not getting as much conversion over into electricity or shaft power.
So the backwork ratio?
We would like it as low as possible because the backwork ratio is how much of the turbine output had to go back and feed the pump. Yeah, we would like that as low as possible. Here's another fluid. Tell me a little bit about the shape of the dome on the temperature entropy diagram. Skewed. Let's say I'm coming out at 125, saturated vapor. What do you think the fluid's going to look like when it comes out? It's going to be vapor. It's going to be what they call dry. It's going to be dry. Okay? Notice also that I'm going to come out at state 2 But look at this temperature at which I come out. It doesn't go all the way down to 25, does it? I can't go all the way down to 25 because this is the line of lower pressure. I have to go from 1 to 2 is through the turbine, and then I have to be at constant pressure and get saturated liquid. So sometimes it doesn't pay to come out dry. It comes out to be moist or high quality at the exit of the steam turbine.
So why is it superheated?
Pardon?
For the state 2, you said superheated.
It is superheated. Yeah.
Sure.
Yeah, we would like to be closer down in this vicinity. But there you go. Notice the backwork ratio is low, 1.9%. Look, notice the thermal efficiency is 19%. Check another fluid, R22. This is a working fluid that's in a lot of residential air conditioning systems. It's been phased out gradually, but it's probably still in a lot of homes. And look at the dome. What do you look at the shape of that dome? Symmetrical. True? And if you're coming in, though, at 125, guess what? You're above the critical point. So maybe I got to figure out where I'm going to stop it at. I don't know where I'm going to stop it at. I can stop it here. I can stop it here. I can stop it here. Where would you stop it at? A, B, or C? Why B? Because when I put it, the isotropic expansion, it gets into the sweet spot being there. Here, it would be A. It's too high. And over here, well, it's too low a quality. Here it's too superheated. Okay. So, but look at this one. I picked it to be 125, the same temperature. I picked it to be about 5,000, so it's somewhere around here for B. And when we expand it, let me look at the entropy. 1.7, 1.72, that's 1.6. This is 1.6, this is 1.7, so about right in here. Oh, I picked that one. I picked it to be saturated vapor at the exit of the turbine. So right there is state 1, right there is state 2, etc. And then it goes like this. Then you boost and then you come up like that. Okay. Notice the backwork ratio, 9%. Add the thermal efficiency, 16%. There's another fluid, isobutane. I even put the dots on for the states. That state is right above the other one. And then you have to cool the vapor before it starts to condense. Then there's two dots right there. It doesn't really show on the plot, but it is, and then they come back up. But here's a plot. R22, isopentane. R11, isobutane. All four of those we just shown. Here's all the temperatures and pressures for the 4 major states. Here are the works and the heats and kind of the bottom line, the backwork ratio and the thermal efficiency for each of these. True? Backwork ratio and thermal efficiency for each of these. Which fluid would you use if you had a 125 degrees C source and you could throw away heat, sink at 25 degrees C? Which one would you use?
That's the highest efficiency and the low and kind of low.
So you liked R11 because the backwork ratio is the low and the thermal efficiency is high. True? Somebody changes it and it says, no, I have now a 145 degrees source and I have to reject at 30 degrees C. You may go through the whole system again, or you may find another fluid that would give you different numbers. Somebody says, well, I don't have a perfect turbine. My turbine is only 85% isentropic efficiency. And then you got to run your numbers, right? And so there's some optimization. But you got the picture. This is good, and this is good. Low backwork ratio, high thermal efficiency. And isn't it surprising how much it changes? I mean, why aren't they all consistent, Professor? I mean, that's a big difference between 2% and nearly 10%. It's the properties of the fluids. Okay? All right. Solar concentrating power. Here, forget the organic Rankine cycle. If you put these heliostats out in the field, which you've probably seen pictures of, and they are oriented such they all reflect to a receiver, and the receiver then really gets pounded. And you may put a liquid metal in there to really absorb that heat. And then bring that liquid metal through a piping system into another heat exchanger or steam drum or something, and maybe you do the loop in for the liquid metal. It's not shown here up to the receiver. Or maybe you bring the water all the way to the receiver and just beat it up. It's going to be hot, 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 hot coming out. Pass it through the turbine, make electricity, have to reject it. If you're in the desert where they like to put these, usually you air cool, so you're not having to supply makeup water. If you're in Texas, you have a lake, and you let some of the water just evaporate off the lake. Or a cooling tower where you have water. We reject a lot of heat into the atmosphere at UTSA in the campus with cooling towers where we're spraying water in and using the evaporative cooling. But you have to provide makeup water. And now the value of water has gone up. And so a lot of states want people to just reject the heat into the air without evaporation. It's less efficient. Engineers like the evaporation. We like the water, but hey, we'll do it without evaporation. Cogeneration, another concept to be exposed to. So you want to make power, but sometimes you also want to provide heat. And a lot of times in a power plant, you have some low-grade steam that's still hot, but it's not going to make a lot of work, but it can be used for some other useful purpose, especially if you live in Chicago or New York or some other major metropolitan area. You can have a steam district which provides steam to many buildings. In the city of San Antonio, we have a cooling district downtown. In the cooling district, there's 2 big plants downtown, and they provide a loop of chilled water to many of the big buildings downtown. And those big buildings say, great, that's great. We don't have to have all that complex infrastructure. We just tap into a pipe. We pull in cold water, cool our building, provide air conditioning, and dump out warmer water into the loop. And that's what happened. It's interesting. For a while, I thought CPS Energy was behind that district cooling in downtown San Antonio. It also does the Alamo Dome. The Alamo Dome's in the loop. But you know what? It's not. You know who does it? Who runs it? SAWS, San Antonio Water System. And so I finally got that straight. I went down to a presentation a couple months ago and was a little bit surprised because I think I've told previous students, it's like, oh no, the city public service, the energy, the electricity providers like to do that because it's more efficient. But what happened was when the Henry B. Gonzalez, they had Hemisphere 68, they were looking and planning the city, and they said, we need to have this for all of these new buildings for Hemisphere 68. I think that was before you were born. 1968. And they found the receptive audience at SAWS, San Antonio Water System. So SAWS got into the energy providing chilled water business. They actually had a steam loop for a while, but then they ran the numbers and they said, you know what? There's very little winter in San Antonio, and it's costing us a lot of money. And they found out how much money they were losing, not making. They were losing, and so they just told everybody, sorry, you have this much time to get out. We're getting out of the steam business, and they did. And the other facilities, they just put in a boiler. They didn't have to put in a boiler because we don't have much need for winter heating of our downtown areas. But if you go to Minneapolis, St. Paul, how long is winter? 9 months. How long is our summer? 9 months. And so they have a lot of need for that. So they just extract some energy out. Something that you should be aware of, we have a great transformation going on in our energy sector. Before, if you were going to build a new electric power plant, maybe 20 years ago, it was going to be, first of all, 30 years ago it was going to be nuclear. Before that it was coal. After nuclear it was back to coal, especially when natural gas prices spiked. But then natural gas prices plummeted because of fracking, not just in Texas, but up in Pennsylvania and New York and West Virginia and all that. So then the energy sector really shifted back to natural gas. And that's where we're currently at. And also, coal is primarily made up of what element? Carbon. And how do you get energy? You take that carbon and bring it with the O2. You burn it. And what goes out the flue, the stack? Carbon dioxide. That's what we wanted for a long time. And so to make a certain amount of electricity, you push out into the atmosphere, not just rejecting some heat, you have to emit some CO2. This is all in the news, but I sure would hate to have anybody pass this class and then somebody ask them a general question and they'd be like, oh, I don't understand that. This is something very important that's going to continue to impact people's careers, engineers' careers that are in the energy sector. So you emit this carbon dioxide into the atmosphere. It was no big deal for many, many, many years. Now you're going to see taxes and limitations, and they're all coming because this leads to greenhouse, global warming. True? Climate change. Okay. So they want to extract somehow that CO2 out of the emission and use it elsewhere. That's a good idea. They had this concept that doesn't sound great, clean coal, as a buzzword for a while, kind of marketing strategy. It basically boiled down to an integrated gasification combined cycle plant. That's a long acronym, but IGCC. And the last, if everybody's not a mechanic ASME member, you should be. As a student, you get it dirt cheap, and it probably carries over with a little transition into the professional member status where it's dirt cheap. I don't know. Anybody ASME member? How much do you have to pay? $20 a year? 20? And you get a magazine. This magazine was October of 2014, a couple months ago. And they talk about coal and the changes that have to be done to try to clean it up. And out of that magazine, well, let me go back. Here's integrated gasification combined cycle. You can look more. It's in the textbook as well as the whole Wikipedia pages. You basically, it's a little more complex, but hey, engineers have to make their money. Is you bring in coal. Where is our coal input? Okay? Where? Somewhere? And you somehow make with oxygen, you make some gas. The gas then goes and is burned in like a natural gas and passed through a turbine. Here is a I'm trying to this right here is a combustor, and right here it goes out hot gases through the combustor, natural gas. Air comes in, it's compressed, you have some fuel coming in. This is synthetic gas, syngas, cleaned up syngas. That comes from this coal stream like that. All right. Now, the goal is, or the idea is, it's easier to clean up a gas than before you combust it than the flue gas as it goes out. You can get mercury out of it, Hg, and you can get some sulfur out of it. Low sulfur coal is good to burn, etc. So you can get those out. You still are stuck with carbon dioxide, but that's separate later. Okay, you have a heat recovery steam generator unit to then try to make steam and pass it through a steam cycle. So that's your combined, like a gas turbine and a steam turbine to make electricity in two places. But you're gasifying coal. You're making coal, pumping it, not burning it straight away. You're gasifying, then cleaning it up, and then putting it through. So you have low mercury, low sulfur content. The other one that you do is you try to, I should show, I'm getting out of order. Okay, go back. Just stay in order. All right. In a minute, I'll talk about what they try and do with the CO2 instead of pumping it into the atmosphere. There's something you can do to it to use it. But the Texas Clean Energy Project, that's a buzzword. It used to be like Texas Clean Coal. This has been around for a number of years, but you can see right there, it's a NowGen integrated gasification combined cycle facility. There's a website you can take a look at. Well, that doesn't seem like it impacts you and me, but it really does, because CPS Energy committed a number of years ago in 2012 to purchase 200 megawatt of electric from that facility, this Texas Clean Coal project. Well, the whole facility was going to put out 400 megawatts. You, the ratepayers in San Antonio and Bexar County, essentially were going to purchase half of the output of that plant, committed to it. It's going to be built by Summit Power Group, $2.4 billion. It's not a small chunk of cane. It's going to have a carbon capture and storage combined with the coal gasification, cleaning up the sulfur, cleaning up the mercury, putting it through a gas cycle, then putting it through a vapor cycle. With that carbon sequestration, what's that mean? You kind of pigeonhole it somewhere. You put the CO2 somewhere that's useful. Urea, that's fertilizer production. And it's going to be completed by, it is not going to be completed by 2015. Wishful thinking. $450 million in funding from the United States Department of Energy's Clean Coal Power Initiative. That's a lot of money. Also, $211 million from, and this is trivia, American Recovery and Reinvestment Act of 2009. Were you too young? What happened in 2009? Somebody new took office. And he said, I need a stimulus package to push this economy. And there was a whole lot of very, very important things in that package. $211 million for this project, and plus some other clean coal initiatives, which are all out there. Anyway, it was all Texas Commission Environmental Quality approved it. It was moving forward, but what happened, unfortunately, is this is where it was going to be located. This is the city, Odessa and Midland. This is San Antonio down here. This is I-10 going to El Paso. So tell me a little bit about this region of Texas. Oil. That's why they're going to do it. They're going to burn coal right in the middle of where a bunch of oil is. So they could take the CO2 and use it for stimulate production of oil in depleting oil reserves. That's not bad. That's a good idea. Only thing is, it happened was between the conceiving and planning and all that, is you just don't find a bunch of fracking going on in this smiley face down here, Eagle Ford, nor in up here to Fort Worth. What's that, Barnett? What's up in the Fort Worth? Barnett? What do you find out here, which is 10 times the size of Eagle Ford? A whole bunch more shale. And there's some UTSA grads sitting in a classroom just like this that were working vigorously out there because they could get outrageous salaries. I don't know what's happened to them since. You know, the energy sector has been shedding jobs left and right. You hear it in the latest jobs reports. But there were a lot of UTSA grads not only working in the Eagle Ford, but out in the West Texas shale. Boom. And I mean a big boom. So everybody was paid a lot of money, but they basically couldn't find the workforce to build this power plant. It's like all the workforce is over doing something else. And plus, natural gas come online a lot cheaper. Burning coal doesn't look so good. Nuclear was going to have a revival. Nuclear's down the tubes again after Fukushima and the price of natural gas going down. But it really was natural gas prices going down more than Fukushima. And so this thing is, I think, mothballed because January of 2014, CPS Energy let their agreement expire. And they backed out of it. And Doyle Beneby, I don't think I quoted him here. He basically said, we don't need to be investing in coal burning in West Texas when we have all this right underneath us, this Eagle Ford shale natural gas. And so that's why they let it expire and they let it go. Also, you can take a look. You'll see this different company, Clean Coal. Clean Coal, buzzword for integrated gasification combined cycle power plant. And it's now dead. This was February of this year. The Obama administration pulled the plug on future Gen 2.0 clean coal power slated to be built in central Illinois. So it's not just West Texas, it's a number of other places. These things are not easy to build. They're still somewhat experimental. And I remember the debate when the CPS said we're going to build some new power plants, we're going to expand our capacity. And this was a number of years ago, and a number of activists get down there and, hey, I'm a ratepayer, I'm a citizen of San Antonio. I want you to invest in clean coal. I want you, CPS, to build the newest, greatest power plant. And I remember it wasn't Doyle Beneby, the predecessor. It's like, hey, we're not a research company. We need to invest in tried, proven technology. And so they resisted going that direction. And given what's happened now, and you could probably find a number of investors who are losing their shirt throughout the United States. Okay? So you're going to find a lot of that. That was probably a very wise choice for you, the ratepayer, because when a utility invests in something and they lose their money, guess what? The rates go up to cover the loss. That's the reality. What's some of the lowest electricity rates in all of the state of Texas? Right here. Right here. Under 10 cents a kilowatt hour. Used to be under 8, but I think it's above 8 now. You go to Houston, pay more. You go to Dallas, Fort Worth, you pay more. Go to El Paso, you pay more. Go to anywhere else. Pretty low in the state of Texas. There is more on this one. There is a small 200 megawatt Polk plant. I don't know the status of it, but it seems to be doing okay in Florida. And this was a pretty good article if you're interested in power production. We covered a lot of ground, didn't we? Next time we have a test. The test will give you about an hour and 45 minutes. I encourage you to be able to solve problems by hand, cycle problems, which has 5, 6, 7, 8, 10 states. So make sure that you can work through and get all your enthalpies, entropies. All right, Savannah's here. You want to make a last statement?